We have completed most of the idea about this exponential growth. We explored y equals ab to the x power. To be growth, we know b has to be greater than 1. Can't be equal to 1. We're going to expand on that just a little bit because there are some other things that can happen. We could have some changes to the time, and what's going to happen is when we see that 1 plus the rate, we're also going to put that over time as we take it to the time equation. Everything we've done before, if you recall all of our questions, which would be super impressive, they were dealing with how many years. Never did we ever change any of those different things, or it was given in days and we put in days. We never changed anything to do with any of those. So a lot of the same similarities you'll see. We're just replacing that old b to the x power with 1 plus the rate. Obviously, we're going to take that percent and put it in decimal form and then putting our time in. The other equation we're going to have, now that we know that e is a number, remember that's the base to our natural log, is we're going to deal with a continuous exponential growth. That means that every second counts. Everything that we're doing is going to count. So we're going to get a continuous growth rate, and that's going to go in as k. T is going to be our time, and A, again, is the initial amount. So we're going to make those equations look a little bit different. So let's just try out a couple of them. So first one, this is going to go after our plain old run-of-the-mill. We're dealing with years. That's compounded yearly, so there's no change to make here. So we have 1 plus 0.08 for our 8%, and we're going to take that to 6 years. Okay. Now, if we want to, we could say that this is going to be taken yearly, so we would say it's over 1. We never do that because it's compounded yearly. But I don't want to say we're just going to do something new. We just didn't need to do it before. So we're really just going to take 500 times 1.08, take that to the 6th power, and strike up your calculator to get your answer. Okay, so that's our basic example. We've done, I don't want to say a ton of those. I feel like I want to say a ton, but I can't say a ton because we didn't do a ton of them. Ton's a lot, right? Alright, so grab your calculator, we'll take care of that. Alright, so here's another one. Value is going to increase at 2% per month. Okay, so here we're not going to change too much, but we are going to deal with this in 3 years. Gotta get the phone. Alright, so we're still going to start with our A value being 1,000. We are going to say that it is increasing, so 1.02. Now this is per month. So to make this a little bit easier, we're just going to make the adaptation. Instead of saying 3, we're going to do 3 times 12 to get 36, and use 36 as our exponent. Just makes that a tad bit easier. Okay. So where does the change really occur? Here's where the change is absolutely going to happen. We're going to compound monthly. We have an account that pays 12%. That is awesome, right? 0.12. We're going to invest $5,000 into that account. So here's what we have. 5,000. We have 1.12, but it's plus the 0.12. How often is it compounded? It's compounded monthly. So 12. So 0.12 divided by 12. We want to know how long will it take for the account to double. Well, what's doubling 5,000? 10,000. All right, there we go. All right, now you're looking at this and you're like, seriously, I'm supposed to solve this for t? Absolutely. All right, divide out your 5,000. Yeah, that means the whole thing equals 2. We have 1 plus 0.12 over 12. All right, so we're going to get a number out of all of this. Okay, I'm guessing we're not going to be able to use the same base. So once we have that number, we're simply going to take the log or the natural log of both sides. Okay, so that's going to bring our t down, and then we're just going to divide out this log 1 plus 0.12 over 12 on both sides. Right, and then we'll get our final value, and it's going to be about 5.8 years. Okay, 5.8 years. Right, so we can quickly get into changing these up and dealing with it that way. Right. These get used a lot in science class because now we have the growth rate constant. right? That's continuous growth. So this is that weird looking equation, right? A of t, right? So the amount based on time. So what do we have going on here? We have 100. Colony starts with 100. So this is our initial value, A. And we're going to take it times E. Well, what's going to be the exponent? Remember, it was continuous growth rate, K, 0.045. And how many there after 5 days? So we're going to say, since we were in per day, we get to just put a 5 up here in the exponent. All right, so we have 100 times E. We're going to take E to the 0.045 times 5 power. Okay, so we're going to put both of those in there. Just make that a little bit easier. All right, follow your calculations, right? 0.045 times 5. We'll do E, use second negative sign, right? That drops that number in there, times 100. We'll get 125. And this is going to be, how many are there? So this is bacteria cells. Okay. Alright, so you can guess where this is going to go. The environment can only support a bacteria population of 100,000. How long will it take? So now we don't know the time, but we need to pull that information back out. So we have 100,000. There it is. We started with 100 of them, remember? E 0.045, that growth rate is not going to change, but the amount of time it takes, that's going to change. So divide out the 100, not the 1,000. So we have E to the 0.045t equals 1,000. And now what we're going to do, since the base is E, we're going to take the natural log of both sides. So this is going to become 0.045t. Again, this is going to be calculator work, so we're going to leave that as is and divide out the 0.045. Right, so calculations hopefully is not a huge deal. We'll deal with that when we're all together again if we need to. So we're looking at 153.5, just over, just after lunchtime there. We'll be able to have those doubled. So that's one of the changes we're going to have. Alright, you can tell this is a Mr. Jansen special. It has zombies in it. I'm like, I'll buy in, that's fine. Zombies are cool, unless they're trying to eat you. Then they're not so cool anymore. Alright, so what do we have? A zombie horde has an initial population of 112, so that is definitely an A value. After 3 days, okay, so 3 times 24, because I see in the end it's times hours. Okay, so we're going to be at 72. So we're going to use 72 for this. It has grown too, so that means it's going to reach a whole different level here. And if you know anything about zombies, they do have a continuous growth rate, and that's what we're trying to find out. So it's going to take 72, but if I want to make this consistent, it's k times 72, just so it looks the way you're used to since this is brand new. So what are we going to do? We can divide out our 112. We're going to be in the ballpark of 28.96 equals e to the 72k. I'm just going to flip those around. Thank you, commutative property. At this point, you saw in the last problem what we're going to do is we're going to take the natural log of both sides, and then we're going to end up dividing this by 72. So our continuous growth rate is going to be 0.0467, and this is per hour in hours, so per hour, in case that makes a difference. Alright, so what is it after 5 days? Oh ho ho! Alright, so we're going to start with 112 zombies, and we're still going to use now our brand new growth rate, 0.0467, and for 5 days that's going to be 120 hours. Okay, so we have to make sure that our units are matching up. So this turned into a little bit like science class. Okay, so we're going to find out what's the actual number of zombies we end up with. And of course, if you know anything about Mr. Jansen and his love of zombies, he wants to know, and is always prepared for, the actual uprising. If the population reaches 7.5 million, there would be no stopping them. Okay. How long does humanity have to rise up against them? So some of the information that we already have is that they started with 112. Doesn't seem like a big number. It seems like we should be able to handle that. They're growing at 0.0467. We want to know how much time do we have. So I'm going to use parentheses here. Not really necessary, but I'm going to show that we are multiplying until we reach 7.5 million. Okay. All right. So repeating calculation that we did before, divide the 112, and after that we are going to start using the natural log. So we're going to take the natural log of this whole big boy right here. And if my calculations are right, just trying to put this together real quick on a snow day, is we're somewhere around 11.112, okay, and we're going to divide that 0.0467, so that's going to give us about 237.94 hours. All right. So obviously, if we want to make sense of that, we're going to divide it by 24. We're going to get ourselves almost at 10 days. So the zombies, they don't move too fast, but they're certainly gonna try and take some things over pretty quickly. All right, so big shout out to Mr. Jansen. Thanks for these awesome zombie questions, and we will all now Google to find out how to stop zombies so we can pitch in and help. All right, make sure you finish up your homework.